Welcome back. So for today, we're going to be talking about latent heat. Latent heat is talking about the heat that's associated with a phase change. So let's talk about phase changes then. There are about 3 phases that stuff exists in everyday world. So there is a solid, there is a liquid, and there is a gas. All right, so you have 3 phases of matter, each with their own different properties. We're not going to get too far into that now, but we do need to just get some vocabulary in here. So for example, if you have a solid that's changing into a liquid, it is melting. So that's that process. Whereas a liquid changing into a solid is freezing. All right. A liquid turning into a gas is vaporizing or evaporating. You can also say boiling, although that typically means you're putting heat under it to make it evaporate. It's the same thing, really. It's just forced evaporation. If you have a gas that's changing into a liquid, it is condensing. And finally, everyone's favorite ones. If you have a solid that is changing into a gas, it is sublimating. And if you have a gas that's changing into a solid, do you remember what this one's called? This is the hard one. And you're disappointed with the answer, I know, because it's solidification. So these are your 6 different phase changes. All right. Now, each one of these phase changes is going to change the amount of energy within the substance. All right. So I drew it in a triangle, sort of. Now, it wasn't even accidental this time. The reason why I drew it in this way is that as you go up, the substance has more energy. So what does that mean? It means that a gas has the most energy, a liquid is in the middle, and a solid is going to be at the bottom. So the most energy is a gas, and the least energy is a solid. If you go through a phase change, going from solid to liquid, that is going to take energy, right? So this is going to absorb energy. And likewise, a liquid to a gas will absorb energy. But if you're going down the gradient, if you're going a gas to a solid, for example, this is going to release energy. All right. So the amounts that are released and absorbed differ depending on the substance, but it'll always be in this situation. All right. So this branch right here, the solidification and the sublimating, that is going to be a bigger change in energy than solids to liquids and liquids to gases. So it's going to be a little bit bigger than them combined, and we'll talk about that right now. Yeah. So let's look at a graph you might have seen before in your favorite chemistry class. So this is called a phase diagram. So what we're going to do is we're going to talk about energy. And we're going to talk about temperature. So let's pretend we're just heating up some water here. So what's going to happen is that as we add energy into our substance, the temperature is going to go up, but then it's going to stop. And it's going to flatten out. Even though we're adding energy, it's not increasing anymore. This is because right now the ice is melting. Okay. And then after that, it's going to go up. Again, after all the ice melts, because it's water, and then it will level off again. This is because it will be boiling. And then it will go up again. Now, these slopes are different. Do you know what these slopes are corresponding to? These slopes correspond to a specific heat of each of the states. So water specific heat is in here, ice's specific heat is there, and the vapor specific heat is that there. So you have three different specific heats. Well, these are actually the reciprocals of the specific heats, but you get the idea. So what's going to happen then is we're going to talk about these flat portions now. This is what latent heat is talking about. There's two types. So it's the energy that's in here. All right, so let's talk about that. So latent heat is the energy change through a phase change. Okay, so how much does the energy change? Now, something to keep in mind here, something that's important, is that the temperature does not change. Temperature does not change while you're doing a phase change. Okay, so imagine you had your glass of ice water, right? So with your ice water, you have liquid water and you have solid water together. Now that's going to be at 0 degrees Celsius because it's a phase change. Now, as the ice melts, it's going to stay at 0 degrees Celsius because the energy is not going into changing the temperature at this point. The energy is changing the phases. It's going into the latent heat of the situation. All right. So there's a formula for this. I'm sure you're not disappointed. The formula is going to be Q is equal to delta H, where H depends, times, all right, so Q is your friend heat. So this is the heat going in or out, depending on which way you're going. So that's going to be in joules. M is mass. Mass is going to be in grams or kilograms. Once again, we are stealing thunder from chemistry, so most of the time we're going to stick with grams. And then H has some choices here. So there's two kinds. You could have HF, which is heat of fusion, or it is possible that you have something called HV, which is heat of vaporization. Okay, so now the only difference between them is if you're going between a liquid and a solid versus a liquid and a gas. All right, so there's two different changes there. If you're boiling something, you have to use the heat of vaporization. If you're freezing something, you have to use the heat of fusion. Now, both of these go either way. Yes, there is a heat of sublimation as well. You're not going to have to worry about it. You could figure it out using the phase diagram if you really wanted to. And that's not what we are going to worry about here. So you're going to have to decide which H value you need and plug that in based off of the situation. We're going to tell you the most important one at least, which is water. Water matters the most. For water, the heat of fusion is going to be 334 joules per gram. So this means every gram of water that you melt it's going to take 334 joules of energy. All right. When it's vaporizing, it's going to take 2,260 joules per gram. All right. So that's the heat vaporization of water. Now, just to give you another substance or two, we also have ethanol. Everyone's friend. Ethanol is at a 109 and an 838, whereas nitrogen is going to be at 25 and 199. So water has a big number here. Water is, once again, a bigger number. The reason for that has to do with its intermolecular forces, which we're not going to worry about it too much here because we're trying to avoid unnecessary chemistry. But that's why it has a high number, because it sticks together. It takes a lot of energy to break apart in multiple stages. So let's do some practice with this stuff. Calculate the heat transferred when that much ice is melted at 0. So we're at the freezing point. We're going to have ice at 0, and then you're going to have water at 0. Is it absorbed or released? So your formula is going to be Q is equal to H times M, delta H times M if you want, if you're into enthalpy, just like in chemistry class, right? So we know the mass is 4.6. We know the H. We have to think about it. If ice is being melted, that means we're going to use H of F, the heat of fusion. So we're going to put 334 there. So we're solving for Q. Q is equal to 1536 joules. So that's how much energy it takes to melt that much ice. Oh, is it absorbed or released? Well, if we're melting, it's going to absorb energy because we're going to a higher state, right? So it's going to be absorbed. All right, let's do another one. Calculate energy transferred when that much water condenses on a soda can at 100 degrees Celsius. Is it absorbed or released? See if you can figure it out. Pause the video. So what we're looking at is Q is equal to H times M. So we're looking for heat. Once again, this time we're doing vapor that's condensing, so we're going to use HV. So we're going to have 2260 times the mass. We know that it's 9.8 grams. Multiply them together. So we're going to get Q is equal to 148 joules. A lot of energy. Now, since water is condensing, it's changing from a gas to a liquid, which means it's going down, so energy is going to be released, right? Because gas has more energy than liquid. So where's the energy going? The substance is losing energy, so that means it's going to be giving it off. It's going to be released into whatever is around it. This is why you really don't want to stick your hand in vapor, because it will condense and burn you. All right, let's do another one. Here's one that's more interesting because it's not water. 99% of the time, you pretty much stick with water, but we like to be the 1%, the ever popular. How much energy is transferred when that much of liquid hydrogen changes to a gas at that temperature? Now, does this temperature matter at all? Nope. It doesn't matter because we are at the boiling point. If you're not at the boiling point, well, we'll worry about that tomorrow. But if you're at the boiling point, you don't need to worry about the temperature because nothing is changing. So we're going to do Q is equal to H times M. So H is, we're changing to a gas. Liquid hydrogen changing to a gas. So we want the heat of vaporization. So 449 times 8.9. And that is going to give us 3,996 joules of energy. Is it released or absorbed? Well, we're going liquid to gas, so we're upping the phase, so it's going to be absorbed. Right? It's going to take in the energy. All right? Just like when you're doing nitrogen. That's why it's so cold, because it absorbs the energy there. So now we're looking at mercury here. Mercury is a neurotoxin that when inhaled can be highly dangerous, blah, blah, blah. This much grams of mercury at this temperature, find the values below, is it absorbed or released? So once again, temperature doesn't matter because we are at the boiling point. So we can go straight to latent heat. So Q is equal to H times M. Now, we're changing to a gas, right? Liquid into a gas. So we're going to go with HV, heat of vaporization, 294. Times the mass, we got 14 grams of it. Delicious. And that's going to equal 4116 joules. All right. So was it absorbed or released? Ooh, what do you think? What do you think? It was absorbed. It was absorbed.